In this lecture, I'll introduce chain conditions. These are certain conditions which taken together will ensure that a module has a Jordan-Holder series. So let R be anything. M and R module. And now we'll define the ascending chain condition. We say that M is said to satisfy the ascending chain condition which is also known as the ACC if for every ascending chain, if every ascending chain of submodules of M stabilizes. So if for every sequence M1 contained in M2 contained in so on of submodules of M, there exists natural number n such that mk is equal to mk plus 1 for all k greater than or equal to n. Or in other words, mk is equal to mn for all k greater than or equal to n. And similarly, we have the descending chain condition, which is defined in a very analogous manner. So we'll define the DCC or descending chain condition. And here we just reverse the containment. So these are two conditions. Together they will ensure that, we'll see that they will ensure that the module M will have a Jordan-Holder series. Let's look at some examples. Z satisfies the ascending chain condition, but not the descending chain condition. Firstly, let's show that Z does not satisfy the descending chain condition. So I just need to find an infinite descending chain of submodules. So here we think of Z as a Z module, or this is the same as looking at abelian group. So here's a descending chain. You just take Z strictly contains 2Z, which strictly contains 4Z, which strictly contains 8Z, and so on. This is a descending chain which never stabilizes. Okay, and the other way, suppose we have M1 contained in M2 contained in M3 is an ascending chain. Suppose at least one of these is not zero. So if Mi is not equal to the zero module for some I, if Mi is zero for all I, then there's nothing to prove, because then it stabilizes right from the first stage. So if Mi is non-zero for some I, then what you can do is you can Mi is actually of the form nz for some n greater than or equal to 1. Okay, so Mi is going to be of this form because this is what all subgroups of Z and therefore all Z submodules of Z look like. So therefore, the set of submodules of M containing Mi which is the same as, which is going to be in bijective correspondence with submodules of Z mod nz, is finite. Therefore, when you look at the modules mi plus 1, this contains a finite number of modules. Only a finite number of modules occur in this sequence. And so, in fact, even if you take this starting from M1, the entire sequence, only a finite number of modules appear in it. And so you can take the largest of such modules. Let M max be the largest such module. Or rather, I should say a maximal module of this kind. May not be unique, and well, it has to be unique because it's a chain. So let M max be a maximal module among these, and if Mn is equal to M max, then this implies that Mn is equal to Mn plus 1, and so on. The rest of the modules have all to be equal to this. And so that shows that the integers satisfies the ascending chain condition, but not the descending chain condition. And now let's look at an example of a Z module that satisfies the descending chain condition, but not the ascending chain condition. So to construct this example, let's first look at the group Q mod Z. So Q mod Z is a torsion group, in the sense that every element of Q mod Z is a torsion element. That is, an element here is of the form A over B plus Z, I guess. It's a coset of A over B plus Z, where A belongs to Z, B belongs to Z minus 0. And if you take this element and multiply it by B, so if I call this X, then Bx is equal to 0 in Q mod Z, because Bx is going to be an integer and get subsumed in this Z. Now we'll define its P primary part. Q mod Z, P is defined to be X belongs to Q mod Z such that P to the nx equals 0 for some n greater than or equal to 1. Or we could say some n greater than or equal to 0 if you like. Okay, so that is a subgroup or a submodule, if you want to think of them as Z modules. I claim that Q mod Z P satisfies the DCC, descending chain condition, but not the ascending chain condition. Well, what you to prove this, you use the following fact, which I will leave as an exercise for you to do. Every subgroup of Q mod Z P is of the form mu pk, which is defined to be x belongs to Q mod Z such that p to the kx equals 0. And so these subgroups themselves, they form a chain. So we have mu p to the 0, which is just the subgroup consisting of 0 alone. You're saying x is equal to 0. Then this contains mu p1, this contains mu p2, and so on. And the union of these things is Q mod Z. So we have only all the subgroups of this group Q mod Z subscript P form a single chain. And so if you have any chain here, it will just take terms from this. Now if you start, so clearly if you have a descending chain, it will terminate, because when you start, if it has any of these elements, you have only finitely many subgroups contained in it. Whereas this chain itself is an ascending chain. So this is an ascending chain which never stabilizes. So Q mod Z P does not satisfy the ACC. However, it does satisfy the DCC, and for this we'll argue, as in the case of integers, suppose you have is a descending chain. Well, it could be that all the entries of this chain are are the full group, full module itself. If mi equals Q mod Z P for all I, then there is nothing to prove. Otherwise, we have mi equals mu p to the k for some k. For some k for some I. So we have at least one term in this series which is a proper subgroup of Q mod Z P. And thereafter there are only finitely many submodules. The series mi contains mi plus 1 must stabilize. Now you could ask, what are the Z modules which satisfy both the ascending chain condition and the descending chain condition? And here's an exercise for you. A Z module satisfies the ACC and the DCC if and only if it is finite. Clearly, if it is finite, then it can have only finitely many submodules, and so it must satisfy the ACC and the DCC. The converse you need to think about why it's true. So if a Z module is infinite, then either the ACC or the DCC must fail. Okay, I'll leave you with that, and in the next lecture we'll see how if you have a module that satisfies both the ACC and the DCC, then it admits a Jordan-Holder series.